Ladies and gentlemen, welcome back to the works of this Seismic Academy. We'll anticipate slightly the topic that will be tackled by Professor Landolfo, professor at the University Frederick II of Naples. He's always been director of the structure department. He also works at international level in many organizations. He coordinates at the European Master of Sustainable Construction under natural hazards and catastrophic events. Professor Landolfo, you have the floor. Thank you. Good afternoon. The topic of my presentation is rather specific. We have listened to very nice presentations on very broad topics, but I will discuss the project of a joint or connection, or more of them. So the topic of my presentation is the connections, and in particular beam-to-column joints. Now, this project was financed by the European Community. So I will discuss this sort of adventure I had the honor of coordinate, which also will have some repercussions on the design tools. And since I'm talking to engineers, I think that you will have some interesting food for thought from my presentation, and some consequences also in terms of regulations. Let us start with a short introduction. Now, when discussing steel structures, the topic of joints is extremely important, even more so if we are discussing seismic safety. And in a seismic prone area, we have to discuss energy dissipation. So connections may or may not have a role in the dissipative behavior of the structure. Steel joints are made in various types, and I will concentrate on the beam-to-column joint, the most important one in steel work and steel structure. So when you discuss seismic stability, in the beam-to-column joints, you have three main components. The panel, the connection, the joint, and the beam. Why do we need to distinguish these three areas? Because clearly the energy dissipation, so plasticization, can occur in one of these three components. Let us see what are the design criteria of a beam-to-column joint in a seismic stability project. Here, this is a solution that we call non-dissipative, a non-dissipative joint. In the case of a very strong earthquake, with very serious conditions on the node, the plastic hinge is formed in the beam, and the connection and the nodal panel are in the elastic area. When a designer decides to use this solution, we say that you are designing a non-dissipative joint. Just in brackets, we design in order to achieve this result in the case of an especially intense earthquake. But the topic today is not just how to design a similar structure, but also how to repair existing structures. So the engineer should be aware of the fact that when the damage actually occurs in the column that has been designed, then you have to repair it, and you have to know how. So this is one of the reasons why you also have other solutions, and the alternative is you localize the plastic damage in the joint. So that's the assumption. This is because it may be easier to repair a damaged joint as against a beam or a nodal panel. So here too we will talk about a dissipative joint, and this is a very feasible option in design, although this is just now at a European level. How do you design in these two cases? How do you design joints for these two scenarios? First, in one case, the earthquake regulations provide for actions according to which you should design the joint. So you have to guarantee what we call the overstrength criterion for non-dissipative connections. So you design for a much higher value than the plastic value for the beam, about 30 to 40%. But how do you design a joint if you assume that it is there that the plastic deformation occurs? So you see the provision is very simple, but at the same time very complex. To satisfy with the Eurocode number 8 says, yes, you can use a dissipative connection if you can show that the plastic rotation of the entire node, is equal to, and you can see there, 25 milliradians or 20, 30 or 34, 35 or 20, 25 or 35, depending on in which case, DCH or DCM. Of course, this is very, very complex, but this solution already exists in other countries. So dissipative connections, for example, in Japan or in the United States, it exists because they have the technique of pre-qualification. So what do? They identify a set of beam-to-column joints, and they invite designers, engineers, architects to use only those. Of course, this means not just choosing a type of joint, but, as you can see from these tables, it also means to comply with other principles in terms of sizes. But the advantage is that at that time the engineer can be sure about the performance of the node and no complicated calculations are needed. Because this is pre-qualification. So there's a limitation to the imagination of the designers or of the engineers with a guarantee of the result. Why can't we use the American solution in Europe? Because the membranes we use are totally different, and because the European seismic risk is totally different from the American one. So it is for these reasons that in 2014 we have launched a research project at a European level with the goal of introducing the concept of pre-qualification at a European level. Now you can see the various partners for this project. There's also a large steel manufacturer. Basically, we tried to achieve this result by combining the numerical side with the experimental side and the theoretical side. All I'm going to show you has to do with pre-qualification of 3 types of beam-to-column joints. And this is just to show you how complex it is. In this slide, you can see the 3 joint types that we have pre-qualified. And in the lower part of the slides, there's another one, just to make a comparison with the American tests. But we shall concentrate on the top 3 ones. So the unstiffened extended end plate joints, the stiffened ones, or hinged joints. So what have we done? I shall try and summarize the various steps of the project. So we started with the design of reference structures and sizing. So first we did what normally an engineer does in design, based on the European codes. We went on with models, a model definition. Then we went back and introduced also sophisticated nodes modeling. And we have applied earthquakes representing the European seismic hazard. This was to understand the effective demand for the nodes and therefore for the joints. So, and then to establish a load protocol that we then applied to the experimental phase. All this was done to pre-qualify the nodes and offer some recommendations for the design and qualification or pre-qualification phase. Just a couple of words on each of these phases. So, pillars, columns, and beams. So first of all, I mentioned the beam-to-column joint, okay? So these are MRF, moment-resisting frames, so-called, but also the possibility of using frames and bracing. This is interesting because the demand on the frame node would be lower because you have the bracing. So these were the types and also various levels of seismic hazard. So basically we identified a series of typical beam-to-column assemblies, one we've called light, then an average one, a medium one, and a heavy one to cover all the possible combinations. Then we went on to the design of the nodes. This was a very specific project because we had to establish certain criteria. It is very important for the engineers to identify the dissipative part, so where the joint damage would occur. So here you have the various options, the various possibilities. We've called these three scenarios. First, the first case, the node and the joint were over-strong, so over-strength. Or full-strength joint. Then plastic deformations in both the connection and the connected beam. And then the third case. Now, these are all possible solutions. It depends on the choice you want to make, so the engineer will have to make a choice. But the most important thing is for the designer, for the architect or engineer to control this solution. And we can then provide the various tools to carry out this solution. For example, for a full-strength joint, you have to establish the design action using a coefficient to modify the plastic strength of the beam. Then look at this slide. I will show you a movie later on. When you have to plasticize the joint, then you have to find a solution to avoid the breakage, the failure of the bolt. This would be a brittle breakage. Now, remember this slide later on when I will show you a movie and you will see the flanges doing exactly what you can see in this diagram. Then the the design of the node and the web panel. Now, the dissipation of the web panel is very stable, or the nodal panel. So this type of damage is difficult to repair. There's loss of verticality in the columns. So the nodal panel should be involved, but not too much. Otherwise, it can be difficult to repair. And of course, we have validated all these various design criteria with FEM. So, as I said earlier, we have developed a model, and this is really a sophisticated model to simulate fully and cyclically the beam-to-column joint. This model was developed at the Coimbra University in Portugal. And we have used this model in the phase when we went back and we have introduced the joint in previously designed projects. So not just the beam-to-column node, because the joint is modeled in very great detail. You see the nodal panel and all these springs, which provide for the cyclical behavior. Then we applied the earthquake to check the seismic demand after establishing a load protocol. And then we went on to the experimental phase, which was one of the crucial stages of this project. Now, we are just discussing 3 types of nodes, and we have carried out about 80 tests. All the tests on the materials, the bolts, and also cyclical tests to feed our numerical models have to be taken into account. Now, some experimental results. Some of these tests were very complex, as you can see, and obviously we have checked all the various requirements, including the Eurocode. So the Eurocode says if the connection plasticizes, you have to guarantee the plastic rotation. So we have applied the European regulations, but also we looked at the American regulations. Now, let us see the first video, which has to do with this solution. This was a node that was designed so as to have fully strength connection, and everything is concentrated on the beam. When the load increases, these are all cyclical tests, with the load protocol, that is the average of the European seismic hazard. Now you see that we obtain the design goal, that is a plastic hinge in the beam, and both the node and the joint are intact. The next test I want to show you is that for a solution that we have called equal strength. Let us see the movie. You can see that the plasticization in the beam is to some extent supported by plastic deformation on the flange of the joint, the lower part. So you will see that the flange, perhaps this is not very evident here, but if you remember the previous slide that I showed you, you can see that also the joint is involved in plastic dissipation. So there's an involvement of the joint in a solution that we have called equal strength. And the last film, this last video, on hunched joints. And the entire plasticization is localized on the beam, clearly in this case. But I would like to show you another thing. Now, we have seen a T configuration only, but we have also done other tests that are represented in these slides. Now, let us see this solution. This is a semi-rigid connection where you do have plasticization with some degree of dissipation, but at the same time, drift and important and significant rotation. So here too we have a video, and here you will notice that all the plastic deformation is concentrated on the beam and flange. As I showed you earlier in the slide. So what we call the T-stab, while the beam remains in the elastic area, the elastic field. So look at the plastic work of the flange without any damage to the beam. Of course, these are all possible options, and therefore engineers must choose based on the goal they want to achieve, and they have, of course, to design consistently with that goal. Then, of course, we have carried out numerical simulations. I will not dwell on this because I don't have enough time. But in the end, we also recommended certain solutions. So we came to the conclusion and said when one or the other solution should be used. We have also created a database in which we have experimental results for our studies and other studies from other parties. So we have been able to provide all the necessary elements for the pre-qualification of these three nodes. And in addition to that, after this project, which lasted 3 years, we have asked the European community to finance a dissemination project, so dissemination of the results. And we have obtained such financing. So our consortium has been extended. In green, you see the initial partners. Now we are twice as many. The goal of this dissemination project was to offer engineers all the tools so that they can apply these rules and the results of our studies. We have also finalized 2 publications. Everything we have done has been translated into 12 languages, so all the main European languages, so publications. We have also developed specific tools for design and planning. The first tool, which is more sophisticated for those who actually want to obtain the cyclical simulation of a joint, we have provided a software tool so that you can have the cyclic response of the joints for advanced analysis. At the same time, we have also created a more practical tool, a first level, let's say, application, which is much faster, and it establishes the sizes of the beam and the column. So once you have the size of the beam and the column, you can design the joint according to the criteria of the design. All this material, as I said, has been translated into 12 languages, and it is free. It is available on this website. You can download it for free if you're interested. This is the website of the metal construction of the European community, where you can have, of the European Union, where you can have all this material. We also have a YouTube channel with all the videos that we've carried out. So you can actually see all the tests. And finally, organizing workshops in all European countries. All the countries in blue that you can see in this map are the countries in which we have held a workshop for the Equaljoint project with all the materials already traduced in the various languages. So we've done about 14, if I remember well, 14 of these. Last but not least, there were 2 workshops in the United States. As I said earlier, prequalification is the rule in the United States. So I had the privilege of being invited to one of these events. This is a convention that is carried out yearly in America. Now, I was invited to present these projects in a connection pre-qualification session of this conference, because they normally use pre-qualification. So we had the opportunity to discuss these topics with our American colleagues. This was the final step of this project, which has been very interesting. In conclusion, this project opens up the way to the concept of pre-qualification. I understand that we Italians don't want to be limited in our imagination. But when we discuss seismic performance and the energy dissipation issues, the relationship between the stiffness and strength of various elements, not all engineers can afford advanced tests and analysis, so pre-qualification is one opportunity, that is to offer engineers a set of possible solutions which are safe in terms of performance. It is not by chance that over the last few months, at a time when most Eurocodes are being revised and reviewed, also including the seismic European code. And I was involved in this panel, which is now discussing a revision of all these documents, and I'm responsible for steel in the process of this revision for Eurocode 8. There will be an annex. This is an example where there is reference to seismic pre-qualification. And here, this annex will reflect the results of the research studies that has been carried out and has recently been finalized with the dissemination step. Now, finally, I would like to thank the team that has allowed us to reach these results, and I would also thank you for your attention.